Hello, my name is Evan Cleveland, and this is Lab 2 for Physics 2. We're going to be looking at more charged tapes. This is essentially a continuation of the previous lab with the same setup and data collection. However, we're going to try and more accurately model the charges on the piece of tape. We're going to use a line array of point charges rather than a single point charge on each piece of tape. Some important physics principles again, F equals ma, and then Coulomb's law in both forms. But also we'll be using superposition in order to analyze charges in smaller segments, and then sum all of those charges, as you would in a Riemann sum. Sneak peek at the results. Tape has a charge of approximately 2.5 e to the negative 8 coulombs, which is much larger than last lab's 1.2 e to the negative 8 coulombs. Big change in the assumptions is obviously we're no longer assuming that the tape is a point charge. This will give us a much better representation of real life. We do have the assumption that the two pieces of tape will have the same charge, but this is almost necessary in order to actually use Coulomb's law without more sophisticated equipment. And then still, air resistance is going to be assumed to be negligible because it would be so small. Here are the visuals for the experiment. We've all seen them, and I'm not going to explain too much of the procedure because we've all done it twice now. But it's here to check the box on the rubric. Here's the good stuff, is the Glowscript. The first section you can see defining some constants. This is my distance between the tapes when one started levitating. And then down here, the commented Q value is the charge calculated from last lab. You'll see why it's commented out soon. But this is the charge calculated using this computational model. Here simply creating a function for the electric field, and then creating the lines of charge that was already given in the script. This section simply creates the tapes, the objects. I've chosen n equals 50 because that's when the runtime started significantly increasing. And then here we are using for loops to iterate through both the top and bottom tapes to calculate the field and force from each point on the top and each point in the bottom. And then we are creating our force vector arrows and printing the results. This is the representation that you get when you run with the point charge Q value from last lab. As you can see, the forces are not balanced. We know that since the momentum of the tapes equals 0, that the force should be 0. The net force should be 0, and therefore the arrows should be balanced. Obviously they're not, so we're going to utilize the program to find a Q value that will get us there. Simply testing different values and going through the numbers allows you to come across a Q value of approximately 2.5 e to the negative 8, which is much larger than the value calculated in the last lab. And when we run with that new 2.5 number, this is the representation we can get. As you can see, the arrows are balanced. Everything looks like it's in order. So the discrepancies between the model and reality. Still, the charges are not actually organized into a single line in real life. To perfectly model the relationship would be very, very hard. I'm not sure if it's possible. However, the charges on the tape are a much better representation. Again, the charges on the piece of tape are likely not perfectly equal. We're assuming they are because they are made from the same process. But if they weren't, then the forces that they exert on each other would be a little different. Some sources of error, discrepancies between the two pieces of tape would affect calculations. In the handling of the pieces of tape, it is likely that they lost some charge as time went on, which could throw off data. What if you had modeled each of your tapes as a single point charge? I feel like I've covered that thoroughly. Essentially, the charge would come out much lower than it actually is in this model. And then why do these estimates differ? Because they're two different models, essentially. We're treating them as two entirely different scenarios. So of course they're going to differ. And we can assume that this model with the line arrays is going to be closer to the real value because it is more accurate to what actually happens when the tapes are charged. In conclusion, using point charge for models for scenarios that don't actually have point charge is not a very good idea. It can result in very poor approximations. It's important to know when to use what model, because sometimes we do need point charge models. But in this case, it's not a good idea. And then superposition allows us to make pretty accurate models of electric fields and forces in scenarios like this.